Okay. All right. So let's go ahead and get started on our third topic for the course, which is chapter 5. Which is called thermochemistry. Okay. So we're concerned here with the connections or the relationship between energy, energy, and chemistry. So a few things that we know. So for example, if you strike a match, you get a flame, right? You burn the match, you get a flame. And that flame is releasing energy into the surroundings. Okay, so we actually have some terminology here. We would call the match a system. And then the surroundings, we call the surroundings. So the air, perhaps your finger holding on to the match. The box that it came in, that's called the surroundings. Okay, so system and surroundings. So the system is typically what we're interested in. So for example, if you have a little battery, well, here's a 9-volt battery. They now make 9-volt batteries out of lithium. So you got a little battery there. So that's what we would call the system. Typically, that's called the system. And then if you connect that to a circuit, you know, it could be anything, whatever. Smoke alarm, I guess. That would be part of the surroundings. Okay, so system and surroundings. Energy. So there's different forms of energy, right? I mean, in here, this would be electrical energy, right? Electrical. Here, this would be what we call heat, right? You can feel it, but there's also light. So there's a couple there. There's heat and light coming out. Those are different forms of energy. Mainly, we're concerned about the transfer of energy. But what we do is we have this idea that there's something which, you know, is a little bit beyond this course, but there's something called chemical potential, which is a form of energy. It's this idea that if you have chemicals, there's some amount of energy that they have inherent in them. And that what we do is we allow these chemicals to undergo reactions so that we can transfer energy out of them. That's typically the goal, right? So if you think about it, if you have a gallon of gasoline, right? So here's our handle, here's our little opening. So like if you've got a gallon of gasoline, we kind of understand, right? There's some energy in there somehow. It's chemical energy, it's right. It's chemical potential is often what it's referred to. And that we're going to get that energy out of somehow. And if you went back, you know, a couple hundred years, what you'd find is there was oil bubbling out of the ground in different parts of the earth, and no one really knew what to do with it. I mean, people figured out you could probably like take some of it, put it in a little lamp and burn it. But for the most part, it was ignored. It was, I mean, it's a pollutant, right? So it like would not be good for the water around there. But people pretty much didn't use it. Just bubble right out of the ground. There was so much of it. And then what happened was people were really using like whale oil in lamps and heating lamps, not heating lamps, and lighting lamps, you know, for nighttime. And they were running out of whales. So once somebody figured out, hey, you can use this oil that bubbles out of the ground. So they started looking for this oil, and it was very profitable. You don't even have to go hunting a whale, right? You think about it, how difficult it is to catch a whale. It's not an easy thing. Instead, just go out to, you know, Pennsylvania and like dig in the dirt a little bit, and this stuff comes bubbling out, right? And all over the country, and then eventually all over the world. So there's chemical energy in that crude oil. It has to be refined to turn it into gasoline. But the goal is to get that chemical energy out of it, right? And so the way we do that typically is by burning it. You burn this chemical, this combination, there's a bunch of chemicals in gasoline, and you burn it to get, generally heat is what you do, but we can also get something called mechanical work, and we'll talk more about work when we get there. Okay, so the first problem that you deal with in ALEX is just kind of looking at the relationship. It's really the issue here is conservation of energy. This is an important idea. So in theory, what we understand of the universe is that all of the energy that exists in the universe today existed at the beginning of the universe. It's just been transformed into other forms. So there was this, gigantic explosion called the Big Bang. All of the energy was in that particle, in that small object. And all that energy has now been transformed throughout the universe. It's a very large universe now, with stars and galaxies and planets and dark matter and dark energy and all this stuff is all there. But the argument is that essentially there's not a creation of new energy. We're not creating, the universe is not creating new energy today or destroying energy. It's just transforming it from one form to another. So a star is a highly organized form of energy, more organized really than the light that it produces. So it's, you're taking this organized energy and you're distributing it in a less organized form. But that less organized form, light, is actually pretty useful. And you can use that organized form to do chemistry, in fact. Okay. So conservation of energy just essentially means that, there's no energy being created or destroyed, it's being transformed. So there's an example that in the ALEX that you work on where you, actually look at an example of this transformation. So here it is. I'll bring it up on the screen here. So using conservation of energy to predict the qualitative. So we're not doing any calculations here. Exchange of kinetic and potential energy. So there's two forms of energy in this context. One is called kinetic, which is energy of motion. So when things are moving, they have energy, right? So a bus that's driving down the road has kinetic energy because it's moving and because it has a mass. So the requirements are really that it have a mass and that it have a velocity, a speed, okay? But then there's another form of energy, which we call potential energy, for lack of a better term, because it's not energy that we can really see happening, but we know it's in there. We have some insight into it based on our experiences, right? You learn this as a baby, right? You learn that if there's something on a table and you try to pick it up and it falls out of your hand, it falls to the ground and crashes, right? And maybe it hits your foot and hurts your foot, right? Or we see a cat and the cat isn't moving and we reach out to touch the cat and suddenly the cat jumps, right? And we're startled by that, right? So that cat has potential energy. It's not moving when you see it, but it does actually move eventually. Oops. Forget what happened there. Oh, I'm sorry. A little crash, computer crash. I'm going to try to restart this up again. Okay. So potential energy is this energy that we don't see actually in action until it is in action, right? Until we actually see it in action, and then it becomes essentially kinetic energy. Okay. So let me just log in here. There we go. May crash again. This computer's getting used like crazy. Okay, so let me just log in here to ALEX. And hopefully, when I screen share again, it won't crash. I don't think I have any apps open. Okay, objectives. And chapter, close out chapter 5. Okay, let's try to share this. Okay, so in this problem, they show you a bicyclist, and the idea is that if the bicycle is moving fast, it has a lot of kinetic energy. If it's moving slow, it has a little bit of kinetic energy. And if it's not moving at all, it doesn't have any kinetic energy. If it is higher up it has more potential energy. If it's lower down, it has less potential energy, okay? So what you're seeing then is that as the bicycle goes down the hill and then back up, it goes faster, right? It's falling down the hill, right? When you ride down a hill, you're falling down the hill. You're trying to control that fall. So as you go down the hill, you go faster and faster and faster. The reason you're going faster and faster and faster is because the potential energy that you started off with is being converted into kinetic energy. And kinetic energy is related to velocity. The faster you move, or let's put it this way, the more kinetic energy you have, the faster you move. So the first question is, where would the bicyclist have the highest potential energy? So again, the potential energy is related to height, right? Because of gravity. It's essentially a gravitational phenomenon. So the higher up you are, the more potential energy you have. So the answer to that first one would be at position F. At position F, you're at the highest level, so you have the most potential energy, okay? This is assuming that we're not like upside down in space or anything like that, right? By the way, you still feel the effects of gravity in space, which is a common misconception. So a satellite or a spaceship or a rocket that is in orbit around the Earth is still being pulled by gravity due to the Earth, and it's still a very strong force, okay? In fact, the International Space Station is only about 250 or 300 miles in orbit above the surface, so it feels a lot of gravity. It's the gravitational force on the International Space Station is not that different from what it is if you're at sea level. It's pretty close, actually, okay? The reason that you don't fall to the surface is because you're moving horizontally so fast that you are falling at the same rate that you're moving forward, so you just end up going around in a circle, okay? Where would the bicyclist have the lowest potential? Okay, so lowest potential energy would be closest to the center of the Earth. And according to this diagram, it looks like the closest you'd be to the center of the Earth is D, right? That's the lowest level. So D would be the lowest potential energy. Where would the bicyclist have the highest kinetic energy? Now that's a little trickier, right? Because you don't see him moving, right? But we kind of have an idea that as you fall, you go faster, 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 right? And then eventually when you hit the bottom, that's when you're going the fastest. Your fastest speed will be at the bottom. And that's when you have the least potential. Then what happens is, as you go back up the hill, that kinetic energy is reconverted into potential. And, one thing I would say about this diagram that could be misleading is that F is above A. So you can't get more potential energy out of the system than you have kinetic to begin with. So that bicycle might be moving really fast as he goes down the hill. He has horizontal velocity. So there's quite a bit of kinetic energy there. So the highest kinetic energy would be at the bottom. So that would be D also, right? Where you have the least amount of potential energy. The highest speed, well, speed and kinetic energy are related to each other. The faster you move, the more kinetic energy you have, okay? So where you have the most kinetic energy, you have the highest speed. So the highest speed would also be at D, right? That's where you have the highest kinetic energy. Would the bicyclist's kinetic energy be higher at A or at B? Oh, I'm sorry, I've got a couple chats here. Oh yeah, very good. Let's see. Highest at B or A. Okay, so it looks like A is higher up, right? B is lower down. So you're falling, you go faster as you fall, right? So B would have more. So exactly, B would have more, you're right. Would the bicyclist potential energy be higher at B or A? Now that, yep, you got it. Higher up, the higher up you are, the more potential, the further away from the surface you are, exactly. And then, okay, now this is an interesting question. Let's look at this one. Would the bicyclist's total energy be higher at B or at A? What do you think about that? The total energy. Okay. Yeah, that's a tricky one. So the total energy is your kinetic plus your potential. You just add the two together. So if you had 5 units of kinetic and 5 units of potential, you'd have 10 total. So A is interest. That's interesting. So A is potential, but again, you can't create or destroy energy in any of this process. So the total energy is actually constant throughout the whole process, right? So if you had more energy at A than you had at B, where did the energy go, right? So let's say I have 10 at A and only 5 at B. Where did that 5 go? Now, in theory, the 5 could leave and go out to the surroundings, right? So that's, in fact, some of the energy is lost as heat. That's true. But in general, this is getting at the conservation law. Assuming we're not losing any energy out of this, A and B should have the same amount of energy. It shouldn't be any different. The total should be the same. Okay, interesting. At any level, actually, A, B, C, D, E, or F. Again, that is making the assumption that we're not losing energy in the form of friction. Okay. Yeah, so at every position, it should have the same total energy, right? That's an important aspect of physics, actually. Okay. Suppose the bicyclist lets off the brakes. So that's actually where you lose energy, is through the braking. You heat up the brakes, and then that heat is transferred to the air. And so actually some energy is in fact lost, but let's take a look at this one. Suppose the bicyclist lets off the brakes and coasts down the valley without pedaling. Okay. So when you pedal, what you're doing is you're taking some of your chemical energy in your body, right, that you've acquired through eating, and you're converting that into, the energy into the bicycle. So, even if there's no friction or air resistance to slow him down, what is the furthest point that the bicyclist could reach without pedaling? Right. So without pedaling, right. So yeah, you got to E, right? Because if you're starting at A and you don't put more energy in through pedaling and you don't lose energy through friction, right? Then what you'll do is you'll go down and you'll come back up right to the level you started off at. And the level you started off at is A and E. A and E, they got the little grid there. So A and E are at the same level. So that's what should happen. Now, in fact, you wouldn't, you could pedal and you could get higher, right? So you could put energy, you could transform energy through pedaling. Likewise, you would actually, distribute some of that energy into the surroundings through heating, which is friction. But what they're saying is ignore those two processes. Ignore the pedaling, ignore the friction. The level you could get off would be E. So there, if you look at level B, there's nothing directly across from it, but you could put like, D plus, so between D and E, there's a level that's the same as B. And so if you started at B, you would be able to get right directly across horizontally, but you wouldn't be able to get any higher, and you, in theory, wouldn't get any lower. Now, again, that's ideal, right? So we know from our own experience that there's friction, right? So some of that energy is transformed into heat. And we also know that we can pedal, or someone could push you, right? So that could happen too. Okay, so there you go. So that's just a little kind of introduction into conservation laws, because when we deal with, heat, heat, enthalpy, work, all of, internal energy, all of those, are subject to these laws of conservation of energy. So we have to kind of get a little intro into that. Okay. This is a physical process we're looking at here, right? This is, we're not really looking at a chemical reaction, even though the energy is initially coming from chemistry, right? It's coming from your muscles, right? So the muscle, those sarcomeres are contracting and expanding and contracting in order to tighten your muscles, in order to make the pedal go around, and that, the energy for that process is coming from ATP. And so it's a whole chemical process, right? Okay, so let me stop share there, and let's come back over here. And let's take a look at the next issue, which is, let me just get this chat out of the way. There we go. We're now going to look at heat and work. Okay. So actually, let me go ahead and I'm going to show you the picture to begin with, so just so you can kind of see this one, and then we'll go through it. So let me stop the video there and share this one. So let's take a look at this one here. Okay, so you see a little diagram off to the right. This is what's called a gas cylinder or a piston. The whole thing is in a water bath, and it's got an atmospheric pressure above it. Okay, so this is a typical kind of setup that we see for this chapter. This is a setup that is kind of connected to the internal combustion engine, which is how most automobiles, there's a switching over to electric vehicles now, but still 95% of automobiles and trucks and almost all ships and aircraft use some sort of internal combustion. And so the idea here is that you can compress gases and get them to burn, and when they burn, they will exert a pressure upward and can also release energy in the form of heat transfer. Okay, so the whole thing is called a cylinder. The cylinder is there at the center. It's full of gases. So those gases are typically air and fuel vapor. So even though gasoline is a liquid, in the automobile, what the engine does is a little bit of it, a small amount of it, is converted into a vapor by essentially spraying it out at high pressure, and it vaporizes, turns into a gas, right? And it's usually hot inside the engine anyways. Once the engine gets started, it's hot, so it vaporizes, it becomes a gas. There's diesel engines where you're actually compressing things to the point where they liquefy, but the typical automobile engine is vapor. So air, which has oxygen in it. Oxygen is the oxidant, the oxidizing agent. And then you've got your gas vapor, gasoline vapor. Notice there's a thermometer in there. So the thermometer is measuring temperature. And there's a pressure downward of an atmosphere. We'll talk more about that later on. And then the piston is that little thing at the top pushing down on the gases. That's called the piston. The cylinder is the container. And then there's a water bath, so there's water. The water is there so that we can measure the temperature. So if the temperature goes up, that means it's getting hotter. And if the temperature goes down, that means it's getting colder. And then there's some sort of device holding the whole thing together, okay? So it says in here, a mixture of gases, of gaseous reactants, so there's reactants, are put into a cylinder where the chemical reaction turns them into gaseous products. So there's some, we're not talking about the chemistry yet. We'll get into that. You actually already know what it is. It's combustion. The cylinder has a piston that moves in or out as necessary. So notice it doesn't say up and down. It says in and out. And the reason for that is that it operates the same way if you rotate it, upside down, right? So if you took this whole thing and turned, I know the water would run out, but suppose it was sealed. If you turned it upside down, then the piston would go down and up, right? Instead of up and down. So we don't want to say up and down. We just want to say in and out. So in means it's getting smaller, so it's coming in. And then out means it's getting bigger, so it's going out, okay? It does this in order to maintain a constant pressure of 1 atmosphere. Let's see, what else does it say? The cylinder is also submerged in a large insulated water bath. The temperature of the water bath is monitored and is determined from this data that 321 kilojoules of heat flows into the system during the reaction. The position of the piston is also monitored, and it is determined from this data that the piston does 335 kilojoules of work on the system during the reaction. Is this reaction endothermic or exothermic? Does the temperature go up and down, up or down? Does the piston move in or out? And does the reaction absorb or release energy? And then how much energy does it absorb or release? Okay, so let me stop share. I'm going to go over heat and work. Okay, so what is heat? Let's start with that one, heat. Heat is the transfer of energy caused by a difference in temperature. Okay, so if one object is at high temperature, so let's say it's at 50 degrees C, and you put it in contact with something that's colder, let's say 20 degrees C, energy will flow from the object that's at higher temperature into the object that's at lower temperature. So we'll call this TH for high temperature, and we'll call this TL for low temperature, right? T for temperature, H for high, L for low. Actually, you know what we'll do? We'll do a C. C for cold. Okay, so this is the colder temperature, and this is the hotter. Now, if they're at the same temperature, energy wouldn't flow. Okay, so heat is the transfer of energy caused by the difference in temperature. And in general, if the bigger the difference in temperature, the more heat that flows. Okay, so if these objects were the same size, the same material, but one was at 21 and the other one was at 20, less energy would flow. And it's proportional to the difference in temperature. So the amount of energy is proportional to the difference in temperature. Okay, so let me write it this way. I'm going to use the symbol Q for heat, lowercase q. So Q is the symbol we're using for heat, is proportional to the difference in temperature, delta T, where delta T is the difference in temperature between the hotter object and the colder object. Okay, so Q. Hope you're familiar with this symbol here. This means proportional to. In other words, it's not equal to, but if you double the difference in those two temperatures, you double the amount of heat that transferred. This symbol over here is called delta. And what it means is change in. Actually, let me not use change in, difference in. Okay, the difference in those two temperatures. So in other words, the amount of heat, the amount of energy, which we call heat, that transfers between the hot object and the cold object is directly proportional to the difference in their two temperatures. So I've expanded that out here. That's the difference in their two temperatures, okay? So again, if if this was 21 and this were 20, that would maybe be a small amount of heat, right? That's not very much. But if this was 100 and this was negative 20, that would be a big difference, right? The difference between 100 and negative 20 is 120 degrees, okay? So that's called heat. And in general, what we know about heat, what makes it kind of useful for us, is that as heat flows into an object, so here's your object, the temperature goes up. The temperature increases. So if I flow heat into an object, it will get hotter, okay? Now the opposite of that is true, the converse, right? If heat flows out of an object, okay, so there's your heat going out, then the temperature will get lower. It'll get colder, right? This is colder. This is hotter. Think about it this way. If you put a pizza in the oven, the pizza gets hotter, right? The temperature goes up. Heat is flowing into the pizza from the oven, and the pizza gets hotter. On the other hand, if you take that pizza and you put it in a freezer, then what will happen is it'll get colder, right? Heat flows out of the pizza and into the freezer, and the temperature of the pizza will go down. So as heat flows out of something, it will get colder, lower temperature. As heat flows into something, it will get hotter, which is a higher temperature. Okay. And let me show one more aspect of this, or some terminology. If heat flows out of something, we call this exothermic. Okay. Exo meaning outside, right? Like an exoskeleton. If heat flows into something, we call this endothermic. I'll use a capital E for that one too. Okay. Those of you in biology probably know the term endergonic, which means energy goes into something, and exergonic, which means energy comes out of something. If we restrict our discussion of energy to just heat, then those terms become endothermic, energy, heat going into something, and exothermic, heat going out of something. Okay, so some processes release heat, they transfer heat out. That's an exothermic process. Other processes, other chemical reactions or chemical processes, heat is absorbed, and we call that endothermic. Okay, so that's heat. The second term we want to deal with here is what's called work. And the symbol for work is a W. This is generally a mechanical phenomenon. We're talking about mechanical energy here. Okay, so for example, if I take a mass and I raise it against gravity, right? You have gravity that's pulling it down. As you raise a mass, so now this mass is up here, we call that mechanical work. Okay, so that's a certain amount of energy required to push or pull that mass against gravity, and that's called mechanical work. There's also electrical work, but we're not going to deal with that. There's also tension work. We're not going to deal with that. There's also there's other types of work. Okay, so that's one. This is gravitational work, right? But it's a form of mechanical. Now, this is the issue of gravity, right? There's another type, which is what we are concerned with here. And this is the one we're really concerned with, which is the idea that if you have a gas cylinder, so remember we have gases in here. We'll go back to that diagram in a minute. And there's a pressure downward, right? We said there's a pressure of an atmosphere, okay? What happens is this. It turns out that compressing a gas, this is called compression. Compressing a gas requires energy. Okay, so now your gases are here, right? So we've compressed them. They're now in a smaller volume. How did that happen? Well, this external pressure is pushing down on them. Okay, so this does what we call mechanical work, and it's called gas cylinder pressure. I'm sorry, gas cylinder work. Okay, and this is what we see with the piston. Okay, now the opposite is true too. It turns out that if you expand the gas, if the gas expands against a pressure, so it pushes this, external pressure, and it expands. This is called expansion. Okay, I'm sorry, let me make that a little bit more clear. Expansion. Okay, so now the gases occupy a big volume compared to what we started off at, right? So this is our second case here. There's also work with that. There's also work. Okay, The only difference between those two is the sign, okay? So by our convention, we have a convention for this. Here, we would say the work is negative. Here, we would say the work is positive, okay? So compressing a gas, pushing it to where it's got a smaller volume, that adds energy to the gases. And so it's a positive change. When gases push the atmosphere away or they push some device away, that's a negative change. So work in that case is negative, okay? So we have a sign, that's called a sign convention, okay? And we also have a sign convention for heat. So what I'm gonna do is I'm gonna make a little table. Okay, so in the first column over here next to the symbols, I'm going to say that we're going to expand the gas, right? So we're doing expansion, okay? If that's the case, then work is negative, okay? If we do compression, so compress the gas, then work is positive. Okay. If heat escapes, okay, escapes the gases, then heat is negative. And if heat is added, then the change is positive. So this is called a sign convention. So work has the sign convention, negative, positive, so does heat, negative, positive. So those are two forms of energy, just like we talked about with the bicycle, that you can have kinetic or potential energy. Here, what we're claiming is that for the gas cylinder, you can have energy go in the form of work or come out in the form of work. Or you can have energy come in the form of heat. So either in or out as the form of heat. So there's two forms of energy. So we're going to call the total energy, we're going to call it heat plus work. Actually, let me write a delta here. I'm sorry. Put a little room over here. Delta E total. Okay, so what's this delta E? This is the amount of energy going into the gases or out of the gases. Okay, if delta E is positive, that means energy went in the gases. If delta E is negative, that means energy went out of the gases. Okay, so you got three terms here. You got your delta E. By the way, most people don't write total there, so you don't have to write total. Most people just call it delta E. That delta, I'm sorry, the delta means difference in, right? We talked about that a little bit earlier. So it's, in other words, the total energy is changing if these are not zero, right? So if this is some number and this is some number and they don't add up to zero, that means the energy is changing, the delta E, right? Or change in energy, okay? So let's take a look at an example. We'll come back to that one, and that will, I think we have enough background on this now to be able to look at that problem. So let's come back to it. So a mixture of gaseous reactants is put into the cylinder where a chemical reaction turns them into gaseous products. The cylinder has a piston that moves in or out to keep the pressure constant at 1 atmosphere. The cylinder is also submerged in a large insulated water bath. That water bath, we're going to use that to measure its temperature to see if energy, heat, is flowing out of the gases or into the gases. Okay. The temperature of the water is monitored, and it's determined from this data that 321 kilojoules, kJ is kilojoules, of heat flows into the system during the reaction. Okay, the system is the gases. So be careful about this. The system is the gases. So when it says that 321 joules of heat flows into the system, what they mean is it flowed into the gases. Okay, now into means you're gaining. So in other words, the gases are gaining 321 kJ, kilojoules of energy. That's a positive change. When you gain something, that's positive. And what we said earlier was that endothermic is positive heat change, right? So if heat flows into something, we call that endothermic, and the heat that flowed in is a positive sign. So positive 321 kilojoules flowing into the gases is an endothermic process. If they had said that 321 kilojoules flowed out of the system, that would be a negative, and that would be exothermic, okay? Likewise, you could phrase it in different ways. If they had said 321 kilojoules flowed into the surroundings, into the water is the surroundings, then that means that the gases are losing the energy, and that would be a negative for the gases, for the system, all right? So in these problems, the gases are the system, the water is the surroundings. Energy that flows into the system comes from the surroundings. So if the gases gain 321 kilojoules, that means the surroundings lost 321 kilojoules. Okay. So that first question, that first, item there is that would be endothermic because it's a positive flow into the system. The position of the piston is also monitored, and it is determined from this data that the piston does 335 kilojoules of work on the system. So does the temperature of the water bath go up or down? Does the piston move in or out? Does the reaction absorb or release energy? And then how much energy does the reaction absorb or release? So here's the deal. The work, the 335 kilojoules of work, that's all about the position of the piston, okay? So mechanical work is a position issue. It's essentially potential energy and kinetic energy. Heat is about the temperature. So anything that has to do with heat, you want to look at temperature, you want to look at endothermic, exothermic. Anything that has to do with position, that's work. And then the heat plus the work, that's the total, okay? So break it up into three components: heat, temperature, work, position, and then heat plus work is the total energy, okay? So we have a choice. We have enough information, having read it, that we could do the second question or we could do the third. Let's do the second one. Does the temperature go up or down in the water, right? Okay, so let's take a look. Does the temperature go, you say, so maybe down? Okay, well, let's see. So the heat went into the water, into the gases, into the system. So that means it came out of the water. So if the water lost heat, you're absolutely right, its temperature will go down, okay? So in terms of heat, energy goes into the gases. That means it came from the water, so the temperature of the water will go down, exactly. If we had a thermometer in the gases, the temperature of the gases would go up because heat went into the gases. But generally, you don't try to measure the temperature of the gases. How are you going to do that? This cylinder is made out of metal. You'd have to there are ways to do it. You can make these special thermometers that are made out of metal, and you can weld them onto the surface. But it's a problem. It's not an easy thing to do. So generally you measure the temperature of the water outside. Yeah, you can use lasers. There's all kinds of cool ways you can do these sorts of things. Exactly. You can actually, it's what's kind of cool is you can actually measure the amount of radiation. Everything radiates energy. We are radiating energy in the form of electromagnetic waves ourselves. And you can see us in the infrared. So if you have a detector that measures infrared, you can actually measure your temperature. Actually, we now have those, right? They now have these IR thermometers, right? So essentially what it does is it measures your radiation profile, and then it can tell what your temperature is. It's awesome. There's cool things we can do that way. Okay, so that's the second one. The third one, does the piston move in or out? So remember, in and out in this context, out would be up, which is expansion. In would be down, which is compression. And what we said was compression is doing work on the gases, so they'll have more energy. Expansion is the gases doing work on the surroundings, and so the work is negative. The gases are losing energy. Okay. So does it move in or out? Well, that we're going to look at the work. The piston does work on the system, 335 kilojoules, right? So if you're doing work on the system, that means the system has more energy. If it has more energy, you've done work on it, that means you've compressed the gases. If you compress the gases, that means that the piston came in, right? It came in, that's compression. So in this context, in is compression. Okay. Yeah. So let me show you a picture of it. Hopefully a picture helps with this. So the idea is, it's all about terminology. So imagine this is our starting point. I'll put it right in the middle, and here's your gases. Now they say it's a pressure, but one way to think about that is you're pushing down. So there's a force pushing down. If the gases are in here, they're pushing up. The gases are pushing up, and the pressure coming down is pushing down. So they're equilibrated. They're staying the same. Okay. So what happens is, if you push even harder, you can compress the gases. So here's what happens. So now our gases are here, right? Okay. So this is compression. And we would say that the piston moved in, right? We would use the term in. So one way of putting this is that the surroundings, which is really the piston, well, the piston is part of the surroundings, did work on the system, which is the gases. Okay, so what's difficult about this problem, it's actually conceptually, it's not difficult. What's problem is they're using so many different words to mean the same thing. So the system is the gases. Okay, so that's in here. The surroundings, which is the piston, is doing work on the gases. When we look at the sign for W, it's either positive or it's negative, right? It's one or the other. It's got to be positive or negative. If it's compression, it's positive. Okay. Compressing a gas gives it more energy. Now, I'm not going to go through the derivation of that. There's, you can go through a calculation relating forces and pressure and height, and you can actually show that, yes, in fact, if you compress a gas or a mixture of gases, they will have more energy at the end than they did at the beginning. Okay. So the piston would move in onto the gases. We would say the piston is moving in. It's just moving in. In means down in this context, right? Okay. And then the opposite. The opposite is where you get expansion. So we'll start this way, and then we'll do expansion. So that's expansion, right? Again, just think like you're pushing down. You're always pushing down, but if it pushes up harder, then it's going to expand. So now we would say, we call that expansion. We would say the piston moves out. Okay. So we would say that the gases, the system, did work on the surroundings. And then remind yourself, the system is the gases, and then the surroundings is the piston. And here, the W would be negative. Okay, so for there, it's negative. For this one, W is positive. And then you'll be okay with that one. Okay, so compression, W is positive. Expansion, W is negative, right? I should point out that that's the convention that chemists use. If you're an engineering major, it's actually the opposite. The engineers actually want to do work on the machine, right? They want the machine to have energy. So for them, if it expands, W is negative, and if it compresses, W is positive. It's actually the opposite convention. But for us, do this one. Expansion, W is positive. Compression, W is negative. Okay. The nice thing in chemistry is we're always looking at it from the perspective of the system, so that'll make it easier. Oh, sorry. Come back to screen share. Let's bring this baby back up. There we go. Okay. So now does the piston move in or out? All you really need to do is look at the sign. You know, the system, it's 335 kilojoules on the system. So that means it's positive, right? So if it's positive work is where you compress, right? Compression, W is positive. You're doing work on the system. So that would be in, right? It's coming in. The only way it could be neither is if there was no work done at all. So they would say that no work was done on the system or the surroundings, on the gases or the piston. And then that would be fine. Okay. Next one, does it release or absorb energy? Okay, now you got to do the total. Okay. So this is where the signs come into play. Okay. If it absorbs, the total is positive. If it releases, the total is negative. Okay, absorbing is positive, like water, like weight. If you're a sponge and you absorb water, that's a positive. Your weight goes up. If you're a sponge and you squeeze it, you release the water, your weight goes down. Okay, so we just have to figure out what those two numbers are. Now we said that the system is gaining 321 in the form of heat, so that's positive 321. Now we're saying that the piston does positive 335 kilojoules of work on the system. So that both of them are positive, right? They're both positive. So if you're adding two positive numbers, that's positive, right? So positive 321, positive 335, you add them together, you're going to get a positive change. So it absorbs energy. In this case, it absorbed energy from the water, right? The water released heat to the gases, so it has more energy that way. And then the piston put energy into the gases as well, so they're both positive. The amount is pretty easy. Adding two positive numbers is very easy. You just got to add them. 321 plus 335 is plus 356, right? 356 kilojoules. I'm going to talk in a moment about the units a little bit. Okay, so 321 and 335. Okay, let me just show one more. Let me come back over here. Oops, I guess I have to hide. Oh, I guess I won't hide it. What I'll do is I'll close this. Hide that. Okay, let me stop share. That will actually help. And move the chat over here. Okay, let's look at one more. It's a cool problem, but there's a lot of terminology in it. Okay. So let's take a look at this one. So this one, getting through that first paragraph, that's just telling you what the situation is. The chemical reaction releases 387 kilojoules of energy. Okay. The position of the piston is monitored, and it is determined from this data that the system does 169 kilojoules of work on the piston. Okay. So now I'm going to look at that last paragraph. The position of the piston is monitored. Okay. It is determined from the data that the system, remember that's the gases, does 169 kilojoules of work on the piston. Okay, now that's work. So that's not heat. So let's not talk about heat. Let's just talk about work. The third question is work, right? The third one, does the piston move in or out? That's an easy one. Now the system is doing work on the piston. So that means that the system is losing energy, right? It's pushing something away. Like if you push something away, you have to use energy to do that. So we would make that negative 169 kilojoules of work. And the piston is moving out. That's expansion, okay? Now, we've got the third one done, but the first, second, and fourth, and fifth questions, actually, 1, 2, 4, and 5, right? There's 5 questions with this. This is a little trickier now because they changed things up on this one. In that second paragraph, it says that from previous experiments, this chemical reaction is known to release 387 kilojoules of energy. That is not saying heat. So be careful. The previous one, they told us about heat. Here, they're saying it's energy. So what they're telling you is the total energy change, delta E total, okay? So it's releasing, that's negative. So the total energy is negative 387. So let me stop share here and come back over here and come back to this equation. Oops, sorry. Okay, we know what this is. They told us what that is. But now they're saying this is minus 387 kilojoules. Right? So if it just says energy, it's referring to delta E. Okay? If it says heat, then it's referring to Q. So in this case, it's negative 387. Releases, right? Releases, that's negative. If it had said absorbed, it would be positive. Okay, so we now know this is minus 387, but we also know the amount of work because it told us that the system does 169 kilojoules of work. So let me bring that in here. This is minus 169, right? Because, I'm going to read it again, the system does the work. That means expansion. And if it's expansion, that's a negative. So now we can get to Q because now we have the other two numbers. Q plus a minus. Plus a minus is the same as minus. Okay, so if we want to know what Q is, we got to add 169 kilojoules to both sides. Okay, I'm kind of explicitly showing you the algebra here. Negative 169, positive 169 is 0. So that means that Q is equal to these two added together. Okay, so one was that 387 minus 169. So what is that? 812. So it looks like it's minus 218 kilojoules. Is your Q. So if it's negative, that means it's exothermic, right? It also means it releases, heat, right? Heat is released by the system into the surroundings. So that means the water will get hotter, and it means the gases will get colder, right? If you release heat, you get colder. What you release it to gets hotter. So let's, what we say was, I have the numbers there, but I'll save those numbers. Let's come back to the picture again. Okay. So is it endothermic or exo? Okay, well, that's exothermic. It's, it's releasing the amount of heat. So we know that it's exothermic. Does the temperature of the water go up or down? So again, because the reaction is exothermic, the temperature of the gas goes down, right? Because it's releasing heat. But where does the heat go? It goes into the water. So the water will get hotter. So the temperature of the water will go up. We already did the piston. Does heat flow into or out? Well, out of, right? It's an exothermic process. So the heat is flowing out of the gas mixture. And then how much heat, we already just did that calculation, which I forgot the number, but let's come back to it. Oh, sorry. Yep, you got it. Thank you. It's, yeah, the negative 218, right? So yeah, negative 218. That was right. Thank you. Interestingly enough, I lost my little picture there. Okay, so negative 218. And let's come back. Let me bring that up there. There we go. Okay, so negative 218. And then, the sig figs are easy here because the numbers they're giving you are whole numbers. So, you can put in 3 there. Okay, and there you go. All right, so that's worded a little bit differently. So be careful with that. You got 3 terms. You got heat, work, and energy. If it's energy, that's your delta E. If it's heat, that's the Q. And if it's work, that's the W. You just have to get the signs. And so work through those. And then I think that's, for the most part, that's the only kind of 2 things you could do. I guess we could give you the heat and we could give you the energy, the total energy, and then you could find the work from that. But essentially the equation's really simple when you think about it, right? It's just a matter of getting the signs right. And unfortunately, if the signs are wrong, then the whole thing's wrong. So you got to be very careful. Make sure you get the signs right. Okay. Let me close that. Okay. So let me I'm going to leave you because this is the last that was the second problem in this section. On Wednesday, we'll pick it up more with the next section. But I do want to talk about energy units because this comes up a little bit later. So the most common unit for energy that you're going to use is the joule, and the abbreviation for it is a capital J. Okay, but there's also kilojoules. You'll see that too. And the abbreviation for that is KJ, K for kilo, right? Remember, kilojoule, kilo just means 1,000, right? So 1 kilojoule is equal to 1,000 joules, right? Okay. So if I have 500 joules, then to convert that to kilojoules, you would just divide by 1,000, right? And so you get 0.500 kilojoules. All right, so there's the unit. Now, what is a joule? So a joule it's a derived unit. This is a derived unit, meaning it doesn't come from fundamental units, from basic units. So a joule is a kilogram times a meter squared per second squared. Okay, kilogram meters squared per second squared. So those are the kind of fundamental units that are used to make up a joule. Okay, and if you take a look at it, kilogram is mass, meter is length, and then seconds is time. So it's related to time. So I can show you, let me just show you real quickly, just a couple of examples of this. So for example, kinetic energy. The general equation for kinetic energy, I'll write it K for kinetic, is 1/2 times the mass of an object times its velocity squared. For this purposes, you could just think of velocity as speed, how fast something is moving. Now, the half doesn't have any units, but mass has units. So what you get is, kilogram is the unit of mass. And then speed or velocity is distance over time. So if you use meters per second, but it's squared, right? We got to square it. You get kilogram times meters squared per second squared, right? And so there's your units right there. And that's your joule, right? So if you put in meters per second for the speed and you put in kilograms for the mass, you'll get out joules out of that calculation. In general, when we do these problems, heat and work are sometimes in joules, but sometimes they're in kilojoules. It just sort of depends on the particular problem. As we move through the chapter, we'll see that we use kilojoules more often, but at the beginning, at least, they're going to be in joules. Okay. All right. So that is sort of the beginning. What we're going to deal with in the next lecture is enthalpy. So we'll go through enthalpy, and then we'll go through calorimetry, and then we'll go through standard enthalpies of formation. So we've got about 3 topics to cover in this. The enthalpy has 4 different types of problems, and the calorimetry has 5. So that's, the big bulk of this we'll start covering. So for those of you that are on campus on Tuesdays, we'll cover a little bit about enthalpy tomorrow. And then for those of you that are not, we will start covering those on Wednesday. I will try, actually on Tuesday, I'll try to upload a video of the lecture on campus. I'll try to get that uploaded onto YouTube. We'll see if it works. It depends a little bit on the technology at Kingsborough, but we'll see if we can get that uploaded by Tuesday evening. Okay, so have a great day. And Abdallah, thank you very much for, putting your responses in this. This was great. Yeah, and you got most of them right too. But it's good to kind of try to interact with this stuff. So good job. And I'll see you later. Yeah, we all need help. We all do. Take care.